For example, do we believe that OIF could work outside of the Southern Ocean in those areas? If you were to pick any of these areas today outside of the Southern Ocean, where would you start? And what data would we have to obtain? What parameters for iron, for silica, for Chaetosaurus density or other phytoplankton communities do we need to find first in order to basically have high confidence in a location? And what data would be so negative that you would exclude a location immediately? So back to the information that we have on those experiments. If we were to choose any place outside of the Southern Ocean to continue to the research, let's say an EEZ zone, what country, which island, which maybe larger country would you in your research prefer? If you could go to a nation and say, nation of Canada, maybe, or maybe it's an island nation in an iron limited area, how would you build a suitability map?
The equatorial Pacific, it can be ruled out because there you have, as I was saying, complex hydrography with upwelling, downwelling, and currents going counter currents this way and that way that are moving around. And there was an attempt to do something in the Marshall Islands, but if you add the R in there, it would be transported out so quickly that the patch would be just gone. You would leave the EEZ, the exclusive economic zone, very quickly. So
just to add a comment on this, so in order to create a contained environment for OIF, you need to find an ocean eddy. And when I understand it correctly, what you're saying is it's very hard to overlap an ocean eddy within an EEZ.
Okay, I don't know the hydrography of the North Pacific. My choice would be the North Pacific. As if you say not the Southern Ocean, then I would say the North Pacific. And the hydrography, the North Pacific, HNLC, it has a shallow Bering shelf to the east. And that is very productive, it's extremely productive region. And then you also have an HNLC on the west of that, to the Russian side, which is very rich in nutrients, but limited by iron. Now, along that shelf, there should be currents, the meanders. Yeah, let's have a look. So,
Okay, so
as I said, I haven't looked at it. Yeah, so go up to the north. Yeah, exactly. Let's have a look. Let's have a look. Let's have a look. About in the 180 line, I think it goes just between Alaska and Kamchatka, right? Yeah. So yeah, there you'll see there is an eddy. It is south of the Aleutian. And okay, you also have eddies. I see now. This is the eddy between the subtropical gyre and the one right across the middle from Japan, going east from Japan. Those are classic eddies, perfect. That warm core eddy just next to the Hokkaido, the island of Hokkaido, Japanese island of Hokkaido, that looks like a promising eddy. But yeah, exactly. But it's an upwelling eddy because it's moving in this direction, means it's throwing stuff out to the left, to the right. Sorry, I'm sorry, it's a downwelling. I just got mixed up from the left and the Southern Ocean and this ocean. But something like that, see, it's like a closed test tube. But I don't know what the nutrient concentrations would be like inside. Which water has been enclosed here? And that you would need to study. But this would be something very promising. I'm excited to see this. I wasn't aware of it. And it's the water is being pushed to the right, right? So it's a downwelling eddy. That means the water is being pushed to the center of the eddy. But it's perfectly closed. And I would be interested to see how deep this column actually goes. It's between the Kuroshio and the Oyashio. The Oyashio is the cold water current coming down from the north, and the Kuroshio is the famous equivalent of the Gulf Stream in the Pacific, with nutrient-poor water, warm water going north. And this one I would guess, it's a parcel of Oyashio water that has been captured by a Kuroshio boundary. I should back down because this is just a gut feeling. Yeah, but if you
so
yeah.
So we should to scout for a potential OIF location, we need to find a suitable eddy.
Okay.
Do these?
See, I'm sorry, you can see that now. It's budded off. Yes, exactly. It's budded off from here, right? It's like so what is a Kuroshio? The warm water, the orange thing which is going across, right? This is the northern rim of the subtropical gyre of the Pacific. So it's warm water and it has captured water from the south. So this would not work because you don't have enough nutrients in that water. So you would need the opposite, going in the other direction. But normally, I'm a bit surprised because in the Southern Ocean, see here, south of it, you also have an emerging eddy, right? This eddy is just going to be pinched off. And this water has got the water from the north. So this would have more nutrients in the middle. Yes, exactly. Than that one. Yeah, okay. I can get, oh, this is beautiful. I didn't know that this was such an energy-rich, eddy-rich zone. But of course, they could do lots of experiments. Japanese scientists could do fantastic experiments here. And also,
so we could go to the Japanese government and let them know that we need some resources to identify the iron concentration and the silicate, nitrate, and phosphate concentration in the eye of the eddy. I think that seems to be very relevant. And then we would also need the permit to add 5 tons or 8 tons or something.
See, if you look at the Kuroshio going east, right? Now there's this one eddy, this down eddy. This is a door. See, the eddy. If you were to look at this also under sea surface height, the sea surface height, it gives you. It's also satellite images. It gives you the exact the height of that water, right? So this eddy that we're talking about here, because it has enclosed warm water, it has from the south. It would be like a pimple, right? It would be like this. Whereas the eddy on the other side of the Kuroshio down there would be like a dimple, because that water is colder than the surrounding water, right? So the eddy to the east, south of this band of water, is a different type of situation. And this is interesting, really interesting, because in the Southern Ocean you also have eddies like that along fronts. But
how stable are those eddies? How stable are those ocean currents? Do they persist for decades, for years?
No, months.
So we need like a live view, and we need to then replan or plan and react to whatever is changing to the ocean currents, correct?
Yeah. So the eddy in the center of the Pacific, further to the right on the image here, the one below, yeah, that one. Exactly, the one below the Kuroshio. That one is going in the other direction, as you can see. And it's an upwelling eddy because it's bringing water up. It's not transporting water from depth, right? But it's just turning it around, and the water in the middle will be colder than the surroundings. So it'll be this dimple. Yeah, so that eddy, I think, would last about a month, 2 months, 3 months, something like that, from its inception. And you can see the different stages of it forming, right? Now, to the left of this image, you see this new one being formed, and that would be pinched off on the left of the image, bordering Japan. Yeah, and then you would see that eddy would have that much of a lifetime. Now, they don't last long because you see when you go towards America, they peter out, right? So you can figure out how long it takes for that water to get there, and then you can also judge how long these eddies last. Now, the real HNFC area would be this one just south of the Aleutians in the middle. Yeah, that one. Yes, exactly. Now, I don't know what the situation. Oh, okay. It's going this way. It's a clockwise eddy, and clockwise means it's piling water up in the middle, and that water being piled up in the middle would be warmer water. So I'm not sure how that would work. But then again, there are other eddies along the Aleutian Islands, and I'm not sure to whom which Aleutian Islands belong to whom, but somewhere there'll be the boundary between Russia and the US and Alaska. Alaska.
So you would either need a permit from Russia or you would need a permit from the US.
Yeah, exactly. And then if you go north again, yeah, in the class, that's the Bering Sea, between Kamchatka and Alaska. And half of the Bering Sea is productive because it's shallow, and the other half, on the Russian side, is very unproductive because it's deep. And of course, here you also have an eddy along the northern Alaskan coast. I didn't know about that. But that strip of land here, this ocean over here is, yeah, okay, so which direction is it going? Oh my gosh. This is like a maelstrom almost. It's a upwelling eddy. I confuse the two. I have the right hand, left hand problem. Anyway, if you look at sea surface temperature and sea surface height, you'll be able to figure out. But just for interest's sake, if you go a little bit back to the Bering Strait, a little bit, yeah, there. So this water now, okay, see this one just north of Alaska. This stretch of ocean here is probably the most productive on the planet. It's the carbon production rates measured there range like 16 gram carbon per square meter a day, which is probably the most productive. The
So
reason,
this is cooling down the planet.
yeah, it's cooling down the planet, but it's also providing enormous food for diatom blooms. And these diatom blooms sink out in the seafloor. And there you have amphipods. Amphipods, these are these crustacea that feed on the bottom generally, right? Most amphipods are benthic, meaning they feed close to the bottom. And there they sit on this diatom ooze, which is lying on the seafloor and in the dense mats, and they are eaten by gray whales. So gray whales, in contrast to the blue whales and fin whales and humpback whales, are coastal, shallow feeders, right? They feed on the sediment surface. And here, this is where they get their food. And the reason why this region is so productive is because it's at the surface waters at the end of the conveyor belt. And the deeper water has very high nutrients. It's also end of the conveyor belt. And these very high nutrients then mix with the iron provided by the Bering Sea shelf. And that's why you have these huge productivity, this very high productivity. And here you can tell from the sediment and so on that those diatom blooms sink out, right? So the current flowing through the Bering Strait is very shallow, it's just 50 meters deep. So that water gets saturated with iron, and by the time it gets to the northern coast of Alaska, it has already built up these huge diatom blooms. So this is natural iron fertilization and very obvious. Yeah, so where else would we go? We could also go along the Canadian coast. Yeah, there. This is where those experiments were carried out, now off Vancouver Island. And yeah, over there in that region. Yeah, so we could do those kind of experiments. Yeah, very weak eddies here. And there's supposed to be one eddy which is formed all the time every year between the northern tip of the island of Vancouver Island and where those two green dots are, that's Vancouver Island. And this island, I forgot the name. I think it's Queen Charlotte Island or something like that. Anyway, so in that region, you also have a fairly stable eddy, and that experiment should be done there.
The big countries seem to lack the education on OIF, so they seem to be opposed because probably they don't understand it. So you really have to study it quite deeply to understand that there are these amazing benefits. And the most other nations do not really have the right location, so they don't really have the right biological or ocean conditions for OIF. So sometimes it's easier to convince smaller nations. So you mentioned, for example, the Marshall Islands. So it is multiple island nations that might be in iron limited zones, and Ocean Visions recently published a map, which is the OIF suitability map, which is adding a few layers of data, and those are like relative weights, and you can read about these weights here. And on what we see right now is just those basic weights. It's like water depth weighted at 10%, and then the photosynthetically active radiation, so like basically sunlight, dissolved iron concentration.
Daniel, this is also unnecessary. I told you that the solar radiation on the northern coast of Alaska is sufficient to drive the highest primary production values recorded on the planet. So you don't have to go to the high radiation zones around the equator and so on to get that. See, this is this confusion that we have. Okay, admitted that the seasonal cycle is going to be shorter, right? Because of the
You just have a few months per year. You just have
yeah,
like
that's right.
December, November.
But
But
in
there you
that
have sufficient. So it's
yeah, but then you know what you have also? You have day length. The day length is much longer there than in the equator. So the angle of the sun is also lower. It's 30 degrees up in the polar regions, in the North Pole or South Pole as well. The highest the sun gets is 30 degrees, whereas in the tropics, it goes up to 90 degrees. But then the days where you have a 90-degree sun, the hours are just 6 because it's between the morning and the afternoon, right? It's 6 hours of 90-degree sun, or close to 90. Whereas up there, you have 24 hours of 30-degree sun. And then if you add up, and this has been done, it shows you have the same amount of radiation. The photon flux is the same in the summer of the North Pole almost as in the equator.
so
Right?
the map that appears after, you can either choose these 4 data points here, or you can extend those data points. I'm not sure, to be honest, if sea surface temperature plays a role. Maybe you could dive into each of those layers of data. And
I don't know what this has got to do with carrying out iron fertilization experiments. There are places where it would work, and there are places where it won't work.
so here, the more green, the darker green is the most suitable area. And if we add these other factors, we get basically this
Okay, this
view.
makes sense. Yeah.
So the question is, and there's some island nations here in these areas. So some of these, so there's no silica layer. So we do not have a good proxy for diatom concentration where there's other phytoplankton. So we don't know if there's any sinkers and or like how deep they would sink. But in your point of view, if we were to create a new suitability map, which data layers are crucial and how would they be needed to configure? So in the data that we've read is the iron concentration is almost like a binary data point. Once you have too high iron concentration, it's not iron limited. So adding the element iron doesn't do good at all. So you just have to exclude and stamp out areas that have high iron concentration. So there's no point in thinking about a certain iron. And maybe you have even the numbers in your head. At what amount of iron there's sufficient iron and you don't need to add any iron. And then if you want to go for carbon export, and that's the primary objective, that the silica layer has to be high too. What, and then obviously if you want to grow any phytoplankton, you need nitrates and phosphates. So that's basically that has to be given too. Some island nations are still around. I think you mentioned Marshall Islands, and there's probably a few others. Do you think it's worth engaging with these island nations? Because an island nation that is benefiting from fishing, and in many of these island nations, fishing is the second or third largest industry after tourism. So for example, in Maldives, I think it's the number 2 or number 3 sector. And so if you were to offer the government, we can increase your fish population. We can also feed, for example, whales, and whales are good for tourism. So more fish is good for tourism. More fish is also good for industry. And we can also export some carbon, which will help you to not sink, because I think many of these island nations will be the first to be at threat from rising sea levels. In my mind, that might be a very compelling pitch to a government. So you get more fish, you get more economic activity, you get more tourists, you get carbon export. You can actually offer your tourists that come and visit your island, if you visit this island, you can have a carbon neutral travel experience. So you can actually come here without some sort of negatives about thinking your personal emissions.
Okay, and then you have to be careful here, because you can go about with the carbon sequestration story. But definitely what would work is you would build up the fish stocks. And that's already enough reason to do all this, just to get the animal biomass up. Because if you then put too much on, this person who carried out the experiment off Canada did, He wanted to have the salmon profiting and take up CO2.
Here, what's the definition of small scale and large scale? So the
Yeah,
largest scale we've seen is 100 tons, and
yeah.
you have done 10 tons, I believe, right? What's large, what's small?
No, large scale would be, you will have to argue about the time scales also, right? So I think this is open to argumentation, right? So large scale would be the entire Southern Ocean or large stretches of the Southern Ocean, where you would take out carbon dioxide in the many millions of tons, right? Many millions of tons. And the small scale experiment would be an experiment that is at the scale to answer the questions you are asking. So if you want to build up the krill population, then you would have to have a patch that lasts at least a year for the krill the krill that emerges from the eggs and that comes up to the surface. The krill eggs sink and they hatch at depth, and then these larvae, they swim up to the surface. And then if they are served a lot of food, then you would have a very high recruitment at the surface, right? And then those krill would again need to be fed continuously later on also, so that they can build up their population. And that would then take a couple of years. So that would be an experiment. It's a question of arguing. You have to apply for these things. You have to have people who are knowledgeable about the background, the scientific background. And for instance, you have to prove that you have done the studies in that area beforehand to show it's not going to do harm and so on. But if you go to the place where this would have the most effect, which is in the Southwest Atlantic, there's so many, so well-studied regions there. We know, we don't have to go there extra and do another study, because what more are we going to find out than we already know? I think we could apply for an experiment in the Weddell Scotia Conference. That's where it would be, where you also have eddies and all that. That's where you could start an experiment. And if you apply for it, and I think the mood is changing, the mood worldwide is changing now that we're seeing the catastrophes. People are experiencing these catastrophes personally. There are only a few outlandish groups or rightist groups and so on that are claiming that there's no climate change going on. But apart from them, it's experiencing it personally, right?
You mentioned these possible islands in Oceania. There's the Pacific Ocean. There's a few of these island nations, the Palawa, Samoa, Fiji, Tonga.
Never thought about them. I can't say anything about them really.
One of the challenges I see personally is that their EEZ zones might be not large enough to cover an eddy. So you need to go get into the eye of the eddy to circulate the iron.
Here you don't see eddies, no? Hardly. If you compare this particular zone, it has very high currents, and these currents are all going in the same direction. And you don't have counterflows. You don't have a current going in the other direction, north or south. So this is pretty soon, after this big orange patch over there, after the Galapagos Islands. The Galapagos Islands are just off just off South America, right on the right of this image. So there you still have a lot of nutrients, but of course very little switch side.
Yeah, so that's South America now, and
no, the Galapagos Islands are just off Ecuador. Yeah, to turn to the left, the whole thing, and to the west. Yeah. So this one orange patch in the middle, right? Yeah, there. By that time, I think the nutrients are gone. And in any case, if you were to fertilize something in one of those islands, that patch would be swept away pretty soon. Like I told you, in the course of 2 weeks, they had about 1,000-kilometer displacement in that time course. 1,000 kilometers, and that's far outside any zone of any kind. This entire girdle around the Southern Ocean is very similar. The places that are slightly different from other places are the Western Antarctic, the peninsula, right? That area into the Atlantic and across, that area is particularly rich and in iron input from Patagonia, but also from the islands there. There are lots of islands there, and the peninsula. It would be logical to start there and build up these species that make resting spores. It's not only Chaetoceros, there's also Thalassiocera there. There's various other genera that also make spores that sink, right? So you have a range of carbon sinkers that, as you continue this fertilization over years, you build up their population. because their resting spots, some of their resting spots survive, the bulk sink out, but some survive. And so they go round and round. In the long term, you are not creating a problem, you are overcoming the problem because you're building up the species populations in the water. The thing about the North Pacific, this is a place where there's a plan to carry out an experiment. But we would learn a lot from it, particularly the effect on the fish, in this case, the salmon. But it's not good for carbon sequestration, or rather, you can't claim much by way of sequestration, because that water that upwells in the North Pacific, it stays there, in a sense, for a long time. So over time, it does get some iron and so on and so on. I mean, you do have sinking out. You don't have that water returning to the deep ocean the way it does in the Southern Ocean, right? It's a much smaller area also, the North Pacific. You could get huge blooms there. I would love to see more experiments, larger experiments carried out for longer in the North, and also to see the response of the zooplankton and the effect on the salmon, for instance, the juvenile salmon that feed over there, how that affects the salmon stock, the salmon biomass. I'd love to see all that. But the amount of carbon dioxide you would remove there is not much because that water stays at the surface, as I said. In the Southern Ocean, the exception about the Southern Ocean is that you have, I think I explained that earlier, you have this water upwelling along the continent, and then it moves north on the way equatorward while it's going round and round, and then it subducts below the other oceans into the Atlantic Ocean, Indian Ocean, and Pacific Ocean, and it takes nutrients with it. So those nutrients are lost in the sense, and they are not utilized for carbon uptake. So that's why the only place where you would really get substantial CO2 uptake is the Southern Ocean.
Yeah. So maybe to summarize, the Southern Ocean seems to be maybe the only suitable area for carbon export. And then other parts of the ocean have maybe little or no carbon export potential, but they do have the potential to grow back fish stocks, to feed the whales, to feed our ocean food web.
Yes, yes, yes. And in the North Pacific, you could also sink carbon because but it's not much because normally you don't have the high nutrients together with high iron. So like a series showed, if you add iron to that water, you do get a big bloom, diatom bloom, and that diatom bloom is going to sink. But the area of that ocean where you could do this is so small that I would be surprised if you had 0.1 gigaton carbon.
But it's still 100 million tons of
100
carbon.
million.
So the beauty of OIF, in my point of view, is the simplicity of execution.
Yeah.
All you need is the iron. Yeah? All you need is to fix iron deficiency. You give the ocean this sort of missing element to grow back diatoms, to grow back fish.
You have to also spread the iron, right? But that can be done with various techniques, no? In the Southern Ocean, you also have the highest wind and the highest current speeds. So you could devise instruments and ships that are not, you don't have humans on them. They could be automated that are spreading the iron, right? So that by going north-south, right? Transects and just releasing iron while they're doing that. All that could be taken care of pretty soon. And then the moment you would just have a tanker, and the tanker would need to just make these circles, and then you